Okay, welcome to the virtual ICM 2022. This is the topology session, and it's my great pleasure to introduce Jacob Rasmussen. Jacob got his PhD in 2003 with Peter Kronheimer in Harvard. Then he spent quite a bit of time in Princeton till 2007 when he went to the University of Cambridge in Great Britain. He has also been a visiting professor at the Simon Center for Geometry and Physics, and he's now going to talk about Floer homology and three manifolds with torus boundary. Welcome.
All right, thanks very much for the introduction. Before I start, I'd like to thank my collaborators, Jonathan Henselman, Liam Watson, and Sarah Rasmussen. Much of what I'm going to talk about is based on joint work with them. And I'd like to apologize to the good people in Copenhagen, where I'd been planning to give this lecture until COVID intervened. I'm really sorry that I'm not able to be there. Okay, so maybe I'll go ahead and start. So I'd like to talk about Floer homology for three manifolds. And to explain what that is, let me first introduce the notion of a TQFT. So what's a TQFT? Well, we'll consider what's called the n+1 dimensional cobordism category, okay, where the objects are closed-oriented n-manifolds, and morphisms are given by cobordisms. So what does a cobordism look like? Looks kind of like an n+1 dimensional manifold with two kinds of boundary components. Say y0 on this side and y1 on this side. Okay. And now if we have two cobordisms like this, say w and w prime, that go from y0 to y1 and from y1 to y2, well, these two copies of y1 are the same manifold, so we can just identify them and get a big cobordism, which we'll call w prime composed with w, going from y0 to y2. Okay. So that's what composition in the cobordism category is. Okay. And now an n+1 dimensional TQFT is some sort of a functor from this cobordism category of n manifolds and n+1 dimensional cobordisms to the category of, let's say, R modules and R linear maps, where R is maybe something like a field or Z typically. Okay. So a motivating example for this definition was the original work of Floer back in the 1980s. Okay. So Floer defined some sort of a functor, which he called I star, from, well, the sort of not the whole category of three manifolds, but just integer homology three spheres in cobordisms between them to the category of Z modules. Okay. And so an important feature of this Floer homology is that it tells you about Donaldson invariants, which are invariants of four manifolds. Okay. So the idea is that if I have a n+1 dimensional manifold, I can think about that as a cobordism from the empty set to the empty set. Turns out that general nonsense will tell you that sort of the TQFT should assign the base ring R to the empty set. Okay. So to a closed n+1 dimensional manifold, we get an element of R describing a homomorphism. Okay. And these Donaldson invariants are invariants of closed form manifolds. Okay. So after the work of Floer in the sort of 1990s and early 2000s, a sort of remarkable simplification of the theory took place, building on the work of Seiberg and Witten and Kronheimer and Mrówka, who replaced the ASD equations appearing in the Donaldson invariants with a different set of equations. And then Oshvath and Szabo, who realized that you could reformulate the theory in a slightly different way to produce something which is now called Heegaard-Floer homology. Okay. So what is Heegaard-Floer homology? Well, it's a functor, again, and it's a functor from the category of pointed three manifolds. So the three manifolds with maybe one or more distinguished points in them, a non-zero number of distinguished points, and cobordisms of an appropriate sort between them. Okay. And so you can work with various rings in Heegaard-Floer homology. I'm always going to stick with F2 coefficients today. So this is a functor from this category to the category of vector spaces over the field of size 2. Okay. And I should point out that establishing the functoriality, genuine functoriality of this construction is fairly non-trivial and involved some work of Juhas and Zemke after the initial work of Oshvath and Szabo. Okay. And thinking again about these cobordisms here, so if I have a cobordism between two three manifolds, I can decompose that into elementary cobordisms corresponding to handle additions. I can add 0 handles, 1 handles, 2 handles, 3 handles, 4 handles. Okay. And it turns out that far and away the most interesting kind of cobordism that you can think about is the one corresponding to a 2-handle addition. Okay. So if I start with a 3-manifold Y and I give you a knot inside of it, and lambda is the longitude of that knot, then I can attach a 2-handle along K with that framing and get a cobordism, let's call it WK lambda, from Y to this manifold here, which is obtained by Dane surgery on K. Okay, so let me tell you a few things about this functor HF hat. Maybe before I go any further, let me say that there are other flavors of Heegaard-Floer homology, but sort of taken all together, this Floer homology for 3 manifolds is far and away the best studied and most interesting TQFT that we know about. Okay. And one sort of surprising fact, surprising thing about this TQFT is that it's very hard to find other interesting 3+1 dimensional TQFTs. So 1+1 dimensional TQFTs, 2+1 dimensional TQFTs, these all come in big families. A lot of examples of these. On the other hand, somehow this TQFT here, coming from Floer homology, is, as far as we know, isolated. And it's a really interesting question if there are more TQFTs like it out there that we just don't know about yet. Okay. So let me say a few words about the properties of this functor HF hat. Okay, one important property of HF hat is that it has a decomposition into spin C structures. So if I take the group HF hat of Y, it's a functor that assigns, I guess, really an F2 vector space to a closed 3-manifold Y, that actually spits as a direct sum over groups that I'll call HF hat of YS, where S is a spin C structure on Y. Okay. So equivalently, you can think about spin C structures as being in bijection with a set H upper 2 of Y in a non-canonical way, or even better with H lower 1 of Y. Okay. And so the second thing that I'd like to point out about this theory is that has a very simple Euler characteristic. So if I fix a spin-3 structure S and take the Euler characteristic of HF hat of YS, well, then I either get 1 if I have a rational homology sphere or 0 otherwise. Maybe the simplest example is S3. That's a rational homology sphere. H1 is 0, so there's a single spin C structure. And this group is just a single copy of F2. So let's make a definition which will be useful a little later on. Okay, so we'll say Y is an L space if it's a rational homology sphere and its Floer homology is simple as it can possibly be, given this restriction on the Euler characteristic. Namely, HF hat of YS is one-dimensional for all spin C structures S. So we've just seen that S3 is an L space. Turns out that, for example, Len spaces or the Poincare sphere, sigma 2, 3, 5, which is +1 surgery on this positive trefoil knot here. Okay, these are other examples of L spaces. Okay, these things that I've written down all have positive scalar curvature. In fact, any manifold with positive scalar curvature is necessarily an L space, but the converse is certainly not true. Okay. On the other hand, a simple example of a manifold that's not an L space is the Brieskorn sphere sigma 2, 3, 7, okay, which is obtained by doing -1 surgery on the positive trefoil. So that has the dimension of HF hat equal to 3. Okay. All right, so now that I've said a few words about this functor HF hat, let's imagine what would happen if we tried to do the same thing again. So say that I was given a 3-manifold, okay, and I'd like to break that 3-manifold into a pair of 3-manifolds with boundary joined together along a surface. And then I'd like to express the Floer homology of the 3-manifold in terms of some invariance of the pieces. Okay, and this idea here falls under the heading of what's usually called an extended TQFT. Okay, so what do? Before I had a category, okay, now I'll form a 2-category where I have n-dimensional manifolds, sigma. Okay, the 1 morphisms in this 2-category are cobordisms, just like I had before, between 2 n manifolds. So here's a 1 morphism here. And then a 2 morphism is a cobordism with corners. So it looks like this. So maybe a sigma is a surface. This is a 4-dimensional manifold with vertical sides looking like sigma 0 times I and sigma 1 times I. Okay. And in a 2-category, there are 2 different ways of composing these 2 morphisms. We can compose horizontally. Or vertically, and stack in either direction. Okay. And so what's an extended TQFT? Well, what I would call a sort of n+1+1 dimensional TQFT is a 2-functor from this 2-category of n-manifolds, cobordisms, and cobordisms with corners to another 2-category whose objects are categories, whose 1 morphisms are functors between them, and whose 2 morphisms are natural transformations. Okay. And this doesn't stop here. We can go on dividing all the way down, but already in the case of Floer homology, this is complicated enough. Okay, so in this setting, for example, if I have a 3-manifold with a single boundary component sigma, well, to sigma I associate a category A of sigma, and to then this M, which I could think about as being a cobordism from the empty set to sigma, I'll get an A of sigma, A of M, which is an object of the category. And then if I were to glue two such three manifolds together along that boundary sigma, then what I would find is that A of y should be the Hom space between A of M1 and A of M2. Okay. All right, so how does this kind of general yoga work out in our specific case of Floer homology? Well, it's been worked out by Lipschitz, Ožvath, and Thurston in a theory which is usually referred to as bordered Floer homology. Okay. And what Lipschitz, Ožvath, and Thurston tell us is that if I start with a pointed surface, sigma with a point z in it, then out of that, I should get a DG algebra A of sigma. And really, I'm lying just a tiny bit here. So this is really a pointed surface together with some extra data, which is a handle decomposition of the surface. And that extra data gives you a sort of specific way of writing down, specific basis for this algebra, if you will. Okay, and then they further tell us that if I have a cobordism from sigma naught to sigma 1, that should give me a bimodule. Okay, A of sigma naught, A of sigma 1 bimodule. Should say A infinity bimodule. Okay. And so what's the sort of category that we're supposed to associate to A of sigma? It's the category of A infinity modules over this DG algebra A of sigma. Sounds a little complicated, but we'll think about it further. And then the functor here associated to this is supposed to be given by tensoring with this bimodule. Okay. So a very nice observation of Denis-Roux is that actually this category of A infinity modules over A of sigma has another name. It's the Fukaya category of the G-symmetric product of the surface sigma minus this point z. Okay, and that's unsurprising, really, if you know the definition of HF hat, but nonetheless quite beautiful. Okay, and before I move on, I'd like to point out kind of an outstanding technical problem in this area of the theory, which is that, so Lipschitz, Ožvath, and Thurston sort of give us the first two rows of the two functor that's supposed to give us Floer homology. But as of yet, this hasn't really been extended to the bottom row to give us a full, honest to God, 2 + 1 + 1 dimensional TQFT. And the problems in doing that are mostly in sort of convincing yourselves that the maps are really well-defined up to canonical isomorphism. Okay. So now I'd like to talk a little bit more about this Fukaya category that Roux introduced into the picture. Okay. And the thing to understand about this Fukaya category is that actually, you know, as Roux described it, it's really just the same as this category of modules that Lipschitz, Ožvath, and Thurston wrote down. So maybe another way of saying it is that Lipschitz, Ožvath, and Thurston wrote down the Fukaya category without explicitly saying that that's what it was. Okay. And in particular, you know, this doesn't really allow you any new ways of computing with this category of infinity modules. Okay. And that's actually something that's worth pointing out and thinking about. Okay, so one important difference between sort of an ordinary TQFT and an extended TQFT is that, you know, we all learn as beginning undergraduates how to compute in vector spaces or how to compute in Z modules. Okay, but typically the categories in which these invariants land are much more complicated. And it can actually be quite difficult to understand what an object in those categories means. Okay. But now, okay, so let's focus on the case where G equals 1. Okay. So now we're imagining that we have a oriented compact 3-manifold with a single torus boundary component. Okay, so then we're supposed to be looking at the Fukaya category of sim1 of the torus minus a point. Well, sim1 is just the torus minus a point. That's an actual Riemann surface. And it would be nice if we could understand the Fukaya category a little bit more explicitly. I mean, informally, we know that elements of the Fukaya category are supposed to be some sort of Lagrangians, and Lagrangians is just a curve inside of this real two-dimensional manifold. Okay, so we'd hope to understand this Fukaya category a little bit more directly. Okay, and to do that, let me first make a comment, which is that we're going to take a covering space of this T2 minus Z. And that covering space is most easily described by taking H1 of the boundary 3-manifold, removing, sorry, this should be removing the integer lattice in there. Okay. And then dividing out by an action of Z. And the thing I'm dividing out by is the kernel of the inclusion of H1 of boundary M into H1 of M. Okay. So maybe the easiest case to think about is when your manifold M is a homology S1 times D2. For example, maybe I have the complement of a knot in S3. Then this covering space, what does it look like? It just looks like an infinite cylinder. Okay, so I have this strip here with its two sides glued together, and I've got a sort of integer's worth of punctures going up the middle. Okay, that's what this covering space looks like. Okay, and so then a theorem that I proved with Jonathan Hanselman and Liam Watson is that there's a well-defined invariant that takes a manifold M like this and assigns to it a object of this Fukaya category, okay, which we'll still call HF hat of M, which we can explicitly think about as a finite set of closed-oriented curves equipped with some local systems, okay, inside this covering space. Okay, in particular, the fact that these curves are closed is in no way guaranteed by the description of this Fukaya category, which naturally also includes some non-compact objects. Okay, and so, well, we can use this invariant to calculate what happens when we glue two 3-manifolds with torus boundary together. Okay, so HF hat of their union, that's supposed to be a Z mod 2 vector space. And well, that's the Hom space in this Fukaya category. And geometrically, all that does, almost all the time, is sort of pull your curves tight into minimal position and count the number of intersections between them. Okay. And let me mention that sort of the key ingredient and proof of this statement is kind of a structure theorem for objects in the Fukaya category as they were described by Roux. And there's a related structure theorem for sort of objects in Fukaya categories of Riemann surfaces due to Haydn, Katsarkov, and Kontsevich. Okay. So what I'd like to do now is just to explain what this invariant looks like in some simple cases. Okay, so maybe the simplest case is when our manifold is S1 times D2. Okay, in that case, the invariant is just a single circle that goes around this cylinder midway between two of these points. Okay. And maybe a more interesting case is when I take the exterior of that right-hand trefoil knot. Okay, then I get a curve that looks like that. Or maybe even more interesting is if I take the exterior of the figure 8 knot in S3, now instead of just having a single component to this curve, I have a union of two components. One looks like the invariant for S1 times D2, and sort of by some sort of poetic justice, the other one is a figure 8 like this. Okay. There are lots of properties of this invariant. Maybe I just want to tell you about one of them, okay, which is the fact that it's, what's the analog of the Euler characteristic? Well, it turns out that the analog of the Euler characteristic here is the homology class that this curve represents inside of Tm bar. Okay. So that homology class actually turns out encoding what's called the Milnor or Turayev torsion of your manifold M. And maybe a more familiar invariant, for example, if M is the complement of a knot, this is really just given by the Alexander polynomial of M. And in general, for example, this Turayev torsion can be computed from a presentation for pi1. It's a very easily accessed combinatorial invariant. Okay, and what's the sense in which this homology class encodes the Milnor torsion is, well, if I look at each of these punctures, I can draw a path from it down to negative infinity in Tm bar. Okay, let's call that, if this is the ith puncture, this is gamma minus 1, this is gamma 0. The ith puncture has a path gamma I going down to negative infinity. And if I let Ni be the intersection number between HF hat of M with gamma I, then the sum of Ni t to the I in this picture will be up to shifting by a power of t, the Turayev torsion. So for example, here for the unknot, all of these intersection numbers are 0. And now this is suddenly 1. And it's 1 forever after. So in this case, I would have this sum is 1 plus t squared plus so forth and so on, which is 1 over 1 minus t. Okay. And it's a good exercise, for example, to do the same thing here and see that you get 1 minus t plus t squared, which is the Alexander polynomial of the trefoil divided by 1 minus t. Okay, so I said that we can use this invariant to compute the HF hat of manifolds obtained by sort of gluing two manifolds together along a torus. Okay, so now maybe the easiest sort of gluing that you can do is a Dane filling. Okay, so that's where I take maybe ET union and S1 times D2. You saw the invariant of S1 times D2 is a straight line. Okay, so for example here, if I wanted to Dane fill in such a way that I got back S3 from this knot complement, the way that I would do that is I would draw a vertical line here. See, there's exactly one intersection point, and that's telling me that HF hat of the Dane filling, which is HF hat of S3, is one-dimensional. Okay. If I were to do the Poincare sphere, which is +1 surgery on this trefoil, then I would draw a line with slope +1. Again, I'd see that it intersected in one point. This is again an L space with a one-dimensional homology. Or if you wanted to do -1 surgery, there I would draw a line with slope -1. Okay, and now you see, indeed, I have 3 intersection points. And that's what I said before was HF hat of the Brieskorn sphere sigma 237. Okay. Maybe a more interesting calculation to make is what happens if I glue together 2 of these exteriors of the trefoil in such a way that I match up meridians with longitudes and vice versa. Okay. The calculation that I need to do there looks like this. Okay. And if I count the intersection points, you see that there are exactly 7. And this is a 7-dimensional vector space here. Okay. And actually, I think it's this calculation that when we first made it really convinced ourselves that this was an interesting way of calculating this setting. Okay. So now I'd like to discuss for a minute or two another invariant that we can get out of this HF hat of M. Okay, and that's an invariant called the Not Floor Homology, which was defined quite a while ago now, independently by Ojvath and Sabo and myself. And that's an invariant of a knot inside of a 3-manifold. Okay, so for example, if I take a knot K and I Dane fill it with slope alpha, so that's taking EK, doing S1 times D2 with it, then I get a knot which I'll call K alpha inside of that Dane filling, which is just the core of the S1 times D2. Okay, and so again, there's a decomposition into spin C structures. HF K hat of K alpha is some F2 vector space. It breaks up as a direct sum. And now the set of spin C structures is in bijection with H lower 1 of EK. If I have a knot in S3, then that's just Z. And again, I can form some sort of an Euler characteristic, which tells me about, which is expressible in terms of the Turayev torsion. Okay, so if I take the Euler characteristic in each spin C structure, write this as a generating function, then I get a factor of 1 minus the homology class of this curve that I filled along times the Turayev torsion. And in particular, this is equal to just the Alexander polynomial of K if, say, K is a knot in an integer homology 3-sphere. And how do I get this Not Floor homology out of our picture? Well, what I do is I pair with some non-compact Lagrangians, which maybe in this picture I would call L0, L1, L minus 1, okay, running between the punctures like this, and with that same slope, alpha. Okay, so for example, here, I see that I have 3 generators to the Not Floor homology. And actually those correspond to, according to these heights, 1, 0, and -1 to T minus 1 and T inverse, which gives me the Alexander polynomial of the trefoil. Okay. And another important feature of the Not Floor homology is that it has differentials on it, which specialize from the Not Floor homology to HF hat of sort of the manifold where we forget the knot and just Dane fill. Okay. And geometrically, what's going on in this picture is just that taking the difference between intersecting with these 3 vertical lines between the dots here and this single vertical line here, where I see a differential. Okay, and that differential here is the differential that appears in Not Floor homology. On the other hand, I could also push this picture the other way and find another differential, maybe let's call it dw, going this way. And again, this is something that we can see inside of the picture for HF hat of our knot complement. Okay. All right. So let me now give a few examples of what typical Hegardt-Floer homologies for manifolds with torus boundary are. Okay. And so maybe let's start with some simple examples. Okay, so here's a definition. We'll say that M is Floer simple if HF hat of N is a graph with respect to projection along some slope alpha. So for example, here I've taken HF hat of the trefoil, unrolled it into the punctured plane, and now if I project with slope 2, you can easily see that this gives me kind of a one-to-one correspondence between the red line down here and the black line up here. Okay, so this manifold is Floer simple. It turns out that this is equivalent to saying that M has more than one L space filling, Dane filling. Okay. And it turns out that if your manifold is Floer simple, then HF hat is determined by, well, the Turayev torsion, which remember is some very classical data about the manifold, and then this single slope alpha. Okay. So we need just a little bit more data than the Turayev torsion to work out this curve. Okay. So maybe at this point, let me ask another question. So which is that if, let's say for simplicity that the homology of M is the same as the homology of S1 times D2, then actually it turns out that every Floer simple manifold fibers over S1. Okay, and it's really quite an interesting problem to try and understand what are the monodromies of these Floer simple manifolds. It turns out, for example, that the Turayev torsion has to have a very special form. So these monodromies must be a quite special subset of the set of all diffeomorphisms from sigma to itself. Okay. All right, so now let me mention a second kind of simple example, which is due to Fagnier. And so this is what are called constrain knots. Okay, so this is a family of knots parametrized by 5 parameters inside of the lens space LPQ. And actually, you should think of these knots as being generalizations of the figure 8 knot, or maybe more generally generalizations of 2-bridge knots in S3. Okay. So in particular, it turns out that HF hat of these manifolds all has a very standard form. It's computable from the Turayev torsion plus a little extra data, and they're incredibly common among simple manifolds. Okay, so one really gratifying thing about being able to make these computations is that we can see that manifolds that are simple with respect to other metrics like hyperbolic geometry are also quite simple in Floer homology. For example, if you were to look at sort of the smallest snap-P census of hyperbolic manifolds, those with fewer than 6 tetrahedra, it turns out that almost all of them are either Floer simple or one-cusp or constrain knots. Okay, so really, actually, we can understand the Floer homology of all of these manifolds and their Dane fillings very well, given only a little bit of data about them. On the other hand, there are also more complicated examples of manifolds. Okay, and a really good source of complicated examples has been satellites of knots in S3. So if I give you, say, a knot in S3, and it's called the companion, and then a knot in S1 times D2, which is called the pattern, okay, then I can glue this S1 times D2 into a neighborhood of the knot to get what's called the satellite knot. So that's illustrating this case, this process in the case when C is the trefoil and this is the pattern. Okay, and the Floer homology of this situation has been much studied by Eftekari, Hedden, Hom, Petkova, Levine. It's a very interesting situation. And in fact, using this, you can get much more interesting curves. Like, for example, HF hat of the exterior of this cable here looks like this. Okay. So in the last few minutes of my talk, I'd like to discuss some extensions of this idea. Okay. And what's the idea behind these extensions? The idea is that we should look for other places where the category that we're thinking about is the Fukaya category of a Riemann surface. And then we can really understand how that category works using curves. Okay. So one example, which is in the case of tangles, is due to Claudius Zebronius. Okay, so if I give you a tangle inside of the 3-ball with 4 ends, maybe it looks something like this, then Zebronius explained how to define some sort of tangle Floer homology associated to that, which is an object of the Fukaya category of the bounding S2 punctured at the boundary points of the tangle. And you can use that invariant to prove that actually the dimension of Not Floor homology is invariant under mutation, which had been quite a long-standing question, sort of 10, 15-year-old question in the field before Zebronius resolved it. Okay. And then the other extension that I want to mention has to do with kind of satellites that we talked about before. Okay. So some very nice work of Wen Zhao Chen, which shows that you can compute the Not Floor homology of a satellite knot from HF hat of, this should be C, the complement of the companion knot when P is a 1-1 pattern. Okay, and also some nice work of Hanselman and Watson, which explains how to compute HF hat of the exterior of a cable from HF hat of the exterior of the companion knot. Okay. And so the last thing that I'd like to say is that we can use this situation as well to define an invariant of knots inside of S1 times D2. Let me call this little HFK hat of P. And it turns out that that basically lives in the Fukaya category of some covering space again. Okay, but now it turns out to be a non-compact object of the Fukaya category. So here, for example, we have 2 spin C structures. Okay, and just like in Not Floor homology, we have differentials. In this case, what the differentials do is they arrange a deformation of this thing into the invariant of what we get when we Dane fill, which is just the solid torus. Okay, and so you'll notice that for this simple P here, these curves, this invariant just consists of some straight line segments between punctures. Okay. So we'll call little HFK of P linear if that's the case. It's a union of these line segments. And then in a purely formal way, it turns out that there's a nice, there's a formula for what the Not Floor homology of the satellite is if this HFK P hat is linear in terms of Not Floor homologies of Dane fillings of the companion. Okay, and now I think I'm out of time and we'll stop.
Thank you very much, Jacob, for a beautiful talk, very clear and beautifully presented. Thank you very much. I think we don't have time for questions, but if there is a discourse online which people might be able to reach Jacob on. So thank you very much again.
Thank you.